Welcome back, guys. It's time for Chapter 5, the rate of change of momentum. So let's go ahead and get started. We're going to work some theoretical ideas, and then we'll talk about some practical strategies. So suppose a particle moves along a curved path, something like this. It could be speeding up and slowing down, and also changing its direction of motion. And the question is, how do we analyze that? So the first thing is to identify a point in the motion that you want to pick as a kind of reference where you want to analyze what's going on. So let's say we decide to pick a point, something like this, and we need to set up a framework, a kind of a reference frame, I guess, to analyze the motion. But it turns out it's useful to consider the net force and the momentum as a starting point for a frame of reference, because you can always resolve the net force into components perpendicular to the momentum and parallel to it. So the way to think of this is the net force and the momentum vector form a plane, and in that plane you can resolve the net force into components perpendicular to the momentum and parallel to it. And the reason we're going to do that is because both mathematically and physically, these two components of the net force have a very different effect on the momentum. And we want to understand that effect, and in order to analyze the problem mathematically, it turns out that resolving the net force vector in this way is useful. So the perpendicular component of the net force is proportional to the perpendicular component of the rate of change of momentum, and the parallel component of the net force is equal to the parallel component of the rate of change of momentum. That makes sense? Let me show you a little demo, a VPython demo, to see how that works. Okay, so here's a picture of a particle under the influence of a force, and let's just watch what happens. The force is just varying in time in some complicated way, and the resulting motion of the particle is some complicated curve, and you can see that it looks difficult, but we want to try to analyze it. So the idea is, first of all, let's look at the momentum. So let's replay the movie now, but with the momentum drawn in. Now the momentum is a blue vector that always points in the direction of motion. And you can see that at every point in time, the momentum and the net force form a plane. In this case, it's the plane of the screen. And we want to analyze the motion by decomposing the force into components parallel to and perpendicular to the momentum. So let's see what that looks like. Now in this movie, you've got the momentum here. The net force is the big green arrow, and the components of the momentum perpendicular to and parallel to the momentum, the components of the net force perpendicular to and parallel to the momentum show up. And so you get a sense of how the thing is going to go. Notice that as the momentum changes, and the net force changes relative to the momentum, the components parallel to and perpendicular to the momentum can change sign. So here, for example, the net force has a component in the same direction as the momentum, so this guy is making the momentum grow in magnitude, and this guy, the perpendicular component, we're going to find out, changes the direction of the momentum, and you can see that as a result, the momentum direction is going down, and it's getting longer. But at this point, the component parallel to the momentum is now in the opposite direction, so it's going to start bringing down the magnitude of the momentum. But the thing is still changing the direction in the same way, so you get a curved trajectory that moves down. So that's kind of how it works. As the relative direction, now the momentum's getting bigger, now the momentum's getting smaller, and so on. But the direction of curvature depends on that perpendicular component. The magnitude of the blue arrow depends only on the component of the momentum that points in this parallel to the momentum. So let's look at that again. But so here it's curving up. Now it's going to start curving down because of that perpendicular component. It's going to curve down, down, down. and then here it switches and starts curving the other way because the perpendicular component is now pointing in the other direction, and so on. But as far as magnitude of momentum goes, we only have to look at the parallel component. So here the parallel component is in the same direction, it's speeding up. Now it's slowing down, slowing down, slowing down, now speeding up again. And now it's slowing down again. So the parallel component changes the magnitude, the perpendicular component changes the curvature. And that's the way that works. Okay, let's talk about the actual components of the rate of change of momentum. Suppose you have an initial momentum vector pointing in some way, and then over the course of some period of time, the momentum changes by an amount delta p. Now I'm drawing the picture big with a large change in momentum in order to clarify the components of the change in momentum. But in the end, we take the limit as the time interval becomes infinitesimal, which means that these relationships that we develop are going to become exact. Let's see how that works. So first of all, there's the parallel component of the change in momentum. Notice that the parallel component of the change in momentum has the primary effect of changing the magnitude of the momentum vector, and the perpendicular component of the change in momentum has the primary effect of changing the direction of the momentum vector. Now I'm interested in rates of change, so what I want to do is to divide each of these by the corresponding change in time, and then notice that the rate of change, the perpendicular component of the rate of change of the momentum, is nothing other than this ratio, delta p perpendicular divided by delta t, and the limit that delta t becomes very tiny. And also, the parallel component of the rate of change of momentum is nothing other than delta p parallel divided by delta t, and the limit as delta t becomes very small. Now let's look at this a little more mathematically. If we define the momentum as the product of its magnitude and a unit vector that points in the direction of the momentum, let's call that p hat. We can write the momentum vector as the magnitude p times p hat. Magnitude p, remember, is a scalar. If I take the derivative of the momentum vector with respect to time and apply the product rule to this product, I get that the rate of change of the momentum vector is the rate of change of the magnitude of the momentum vector times a unit vector that points in the direction of the momentum. That's the parallel component, and so we can think of that as dp dt parallel. How do I know it's parallel? Well, it points in the p hat direction, so it's got to be parallel to the current momentum. And then the other piece, which is the magnitude of the momentum times the rate of change of p hat, has got to be the perpendicular component. Now, we'll see in a moment geometrically how dp hat dt happens to point perpendicular to p hat. But suffice it to say that dp hat dt and p hat are perpendicular to one another. So looking at this again, if I have a momentum vector that points in a certain direction, p hat is the unit vector that points in the same direction. Delta p is some small change in the momentum. Delta p parallel, which is the magnitude of delta p, or the change in the magnitude of the momentum vector times the unit vector that points in the momentum direction. That's delta p parallel. Delta p perpendicular is the magnitude of the momentum times the change in p hat. And of course, again, I can divide these guys by delta t, and you can see the connection between dp dt parallel, dp dt perpendicular, and the rate of change of the magnitude of the momentum and the rate of change of the direction, the p hat vector. All right, let's keep pushing on this. So I went ahead and put the mathematical definitions of dp dt parallel and dp dt perpendicular back at the top. I'd like to look at this thing geometrically. So what I've got here in this picture is a particle moving along a curve with a radius of curvature capital R. And we've got p initial hat and p final hat. Remember, these guys are unit vectors, so they have exactly the same magnitude. And notice that the change in p hat is a small vector, and in the limit that time interval becomes small, you can see that this small vector, delta p hat, is going to be perpendicular to p hat. Notice that there's an angle theta. Theta is the angle through which the thing has gone. It's both an angle in real space and an angle between the two p hat vectors. It's the same angle because as the particle moves along the curve, both the r vectors that go from the center of the circle out to the position of the particle and the p hat vectors turn through the same angle since they're perpendicular to one another. And you can see that therefore we have two similar triangles. There's the p hat triangle that has delta p hat as the small side and p hat initial and p hat final as the long sides. And then the space triangle, the actual physical space triangle, which has the distance traveled by the particle, that's the magnitude of the velocity times the change in time, and it's got the radius of curvature of the curve as the long side. Now, if these are similar triangles, which they must be, because theta is the same for both, and they're both basically isosceles triangles, right? So it means that delta p hat over the magnitude of p hat must be the same thing as v delta t divided by r. Now the magnitude of p hat is 1 because p hat is by definition a unit vector. And so I can simplify this thing and take the limit as delta t goes to 0. And what I get is that dp hat dt is a vector perpendicular to p hat with a magnitude of v over r, because you can see that the delta t went away because I turned it into dt. So what that says is that the magnitude of dp hat dt is always just the velocity of the particle divided by the radius of curvature. And there's nothing specific to low speeds about this. So this is actually even true at relativistic velocities. Now let's take that and put it back in. First of all, I want to remind you of the momentum principle, that dp dt is the net force. You can think of resolving the net force into the parallel and perpendicular components of the force. So for example, if you have some comet moving around a star, the net force, of course, is gravitational, and you can always resolve the net force into the parallel and perpendicular components, parallel and perpendicular to the instantaneous momentum of the comet. The idea is that the parallel component is the rate of change of the magnitude of the momentum times p hat. The perpendicular component is the magnitude of the momentum times the rate of change of p hat. But we just worked out that the magnitude of the rate of change of p hat is v over r, and so we can write out that the perpendicular component of the force is the magnitude of the momentum times the ratio v over r. Now, the one thing I haven't done here is to specify the direction of the perpendicular component, but it always points toward the center of curvature. If you go back to the geometry from the previous slide, you can see that it always has to point toward the center of curvature of the curve along which the particle is moving. So I'll just say in vague terms, toward the center. Okay. Now, what do we mean by r? If a particle moves along a curve, if I imagine analyzing the motion at a particular point, r, there's no circle in this picture. The particle is just moving along some curve, but r is the radius of curvature of the circle that matches the curvature of the curve at the point in question where you're actually doing the analysis. So that's called the kissing circle because it matches the curvature of the curve like a kiss, and the radius of curvature of that circle is the same as the radius of curvature of the curve at that point. All right, very good. So now, the question is, that's all very theoretical. We've got some theoretical ammunition here to solve problems. But the question is, how do we actually solve problems? So I've got a few hints for you about how to do that. First of all, I want you to watch the Free Body Diagram podcast that I posted to ACE. It goes through in detail explaining how to draw free body diagrams, how to identify forces, and things like that. And it goes through 2 examples in detail where there is changing momentum. Now, they are both, these particular examples in the free body diagram podcast, are both straight line motion. There is no curved motion. But we'll get a lot of experience with motion along a curve in this chapter. But there are both good examples of situations where there is a rate of change in momentum, at least. The one thing is, I created that podcast for a course that used the more traditional language. And so where the podcast says Newton's second law, I want you to think momentum principle. The podcast uses mass times acceleration. We use rate of change in momentum. It's the same thing at low speed. Rate of change in momentum, it turns out, is actually more general because it also works even at relativistic speeds. But for the purposes of a lot of the examples we'll be doing in this chapter, you don't need to worry about the relativistic situation very often. There's another thing that shows up in the podcast that's relevant, and it's the fact that when one object pushes on another object, the second object pushes back with an equal and opposite force. We know that as reciprocity, but the traditional physics curriculum calls that Newton's third law. It is Newton's third law. It's just that in this textbook, the textbook we're using, that's called the reciprocity principle. So if you just make those substitutions, everything else is okay. So I thought the easiest way to show you how to do this was to actually work out a complete example. This is an example of pulling a loaded sled with a total mass of 40 kilograms at a constant speed in the x direction, using a rope that's at an angle with the coefficient of friction between the snow and the sled. And the question is, what's the tension in the rope? So the idea is to draw a free body diagram. So there's my sled. You don't have to be an artist. You just have to have a diagram that indicates what the thing is. There's the snow. And then we have to start identifying forces. So we've got a tension. That's the force of the rope on the sled acting at an angle of 35 degrees. Then we've got the earth pulling down on the sled. We can call that the weight force of the earth pulling down on the sled. Then we've got the snow pushing up on the sled, the ground pushing up on the sled. Sometimes that might be called a normal force. It's kind of the mattress force I always talk about. It's the squishing of the atoms. And then there's the friction between the ground and the sled, and the friction is going to oppose the motion. Now, I'm assuming there's a constant velocity to the right in the same direction as the pull of the rope. Excuse me. But the snow is going to oppose that with a force that goes to the left. So the first thing to do after you've identified all the forces and drawn the free body diagram is to write out the momentum principle. And the momentum principle says the sum of all those forces, the normal force plus the frictional force plus the tension plus the weight, has to equal the rate of change of the momentum of the sled. Now in this particular example, the rate of change of the momentum, of course, is 0 because the sled is moving it with a constant speed in a straight line. In problems where that is not true, where the speed is increasing or decreasing, or where the motion is not in a straight line, then the rate of change of momentum is not going to be 0. And you're going to have to figure out what it is based on what's happening in the problem. But in this case, it's going to turn out to be 0. Now, after we've written out the momentum principle in vector form, I like you to write each component as a separate equation. So let's look at the x components, the horizontal components of these forces. First of all, there's the x component of the normal force. There's the x component of the frictional force. There's the x component of the tension, and the x component of the weight. Those have to equal the x component of the rate of change in momentum. But you can see the normal force points straight up. So that means that the x component of the normal force is 0. Likewise, the weight points straight down, so the x component of the weight is 0. And finally, the momentum has no rate of change in either x or y direction, so its x component is definitely 0. We can also put in that the frictional force has a negative x component, so I can just write that as minus F, where F is the magnitude of the frictional force. And the tension is directed at an angle, so that means the x component of the tension is the magnitude of the tension times the cosine of 35 degrees. And those guys have to add up to 0, so that's one equation. Now let's look at the y components. Again, I have the y component of the normal force, the y component of the frictional force, the y component of the tension, the y component of the weight is equal to the y component of the rate of change of momentum. Now, in this example, in this component equation, the frictional force has no y component, and the rate of change of momentum is still 0, even in the y direction and in the x direction. So I can get rid of those right out of the box. The normal force, however, is not 0, and it has a positive y component. The tension is not 0, and its y component is t times the sine of 35, or the way the authors in the book do it is the cosine of 90 minus 35, which is the same thing as the sine of 35. And of course, there's the weight, which has a negative y component of mg. And those guys have to add up to 0. So let's reorganize here a little bit. Okay, so what about that frictional force? Now we know that the magnitude of the frictional force is equal to the coefficient of friction times the normal force. This is for kinetic sliding friction, so it's the coefficient of kinetic friction. But because the sled is moving with a constant velocity, there's no ambiguity here. The thing is definitely sliding. So we can simply write F is equal to mu times n. I can also solve the equation on the right for n, and I get n is mg minus t sine 35. So substituting in the friction and solving for n on the right, notice I've got two equations, each with two unknowns, n and t. But the standard strategy for dealing with a situation like that would be to simply solve one equation for one unknown and substitute into the other. So I'll do exactly that. I'll take the expression for n on the right and substitute for n on the left. And now I have a single equation with t as the only unknown. I can expand the binomial on the left, collect terms with factors of t, and then factor the t out. I end up with something like this. And then I can just solve for the tension. And you can see that it comes out as 84 newtons. And this is also done in the textbook, in the example. You can take a look at that. But that's how it's done. So the idea is you make a free body diagram, you write out the momentum principle in vector form, you break it into components, and then you solve for the variables that you're left with. And that's the end. We'll see you guys next time.